Thank you, Brad. Thank you, everybody, for coming back and sticking for the next 25 minutes or maybe more. I hope that it will not bore you to death, but I'm the last one to present, so I will try to make the best of it. So today I'm going to talk about delivery of STLTP seamlessly over multiple links. To present myself, I'm Rozenberg. I'm the CTO and co-founder of VideoFlow. And if you haven't been participating in the VSF, I'm a regular feature lately. So let's go on with the presentation. So today I'm going to outline the studio to transmission link in ATSC 1.0, moving to an all IP with ATSC 3.0. I'm going to touch base on the new kids in the block, the STLTP, the RPTP, and the DSTP, what those crazy acronyms. What's so special about them? Why reliable delivery is so important? Deployment options like point-to-point and SFN, and full scale, I have a typo, Lighthouse for an ATSC and ATSC 3.0 and ATSC 1.0. So let's start with the standard STL. STL, to those who are not familiar, it's a new and it might be considered as an exciting new opportunity or a capability that we usually don't touch based upon on this session. The STL stands for Studio to Transmitter Link. We have a studio, which is a local TV station. They have an ASI or 31M signal going to a microwave transmitter, receiving that feed, transmitted over long distance to a receiver. Then it outcomes as an ASI to an exciter and then to an HVSB transmitter. That is the traditional STL that was deployed in the last 20 or so years. Now we are coming and enhancing that. How do we do that? We're enhancing that with a standard IP. The IP comes as a backup, and we use a reliable delivery protocol like RIST or SRT or ZigZag, whatever you wish to use, and you use a backup of an IP layer to back up the STL. We have still the traditional microwave, but now we can supplement that with a green link going through. We have an AS on the transmitter side. We have the ASI coming in. We have the IP backup. We can either do a failover between them, or with some techniques, we can do seamlessly switching so that we have a continuous feed going to the exciter. And why is it so special, and why do you need that? You need that because microwave is still sensitive to interferences of harsh weather, or to those who are familiar more in those in the Floridas and the southern states, they are suddenly hit by lightnings or lightning storms, and they are going out of commission, and we need to have business continuity. So adding an IP layer or an IP link can supplement that and continue the business as if nothing has happened. That becomes more and more important now during the recent COVID pandemic. Now the new kid in the block, in the recent 2 years or so, we've been hearing about ATSC 3.0 or next gen TV, and people are talking about it. It's heavily pushed in the USA. I'm not going to explain the entire ATSC 3.0 ecosystem. For this, the audience need to turn to the ATSC organization, but I am going to touch base on some practical aspects of connecting reliably, and the type of deployments that you might expect or see in the coming years, and where reliable delivery is a very important partner of that. So new acronyms come into play, and don't worry, I'm going to touch base on every one of those. But this is a slide that I took from an ATSC standard or specification showing it up a system. Unlike ATSC 1.0, ATSC 3.0 went a full all IP. We have data layer, that is the data delivery, data sources coming in. We have a application layer and coming in. And then it is transmitted as an STLTP over the microwave to the transmitter and going upwards to the RF. And let's explain each and every one. Now I'm going to touch base on the three specific newcomers and then explain how do we use them. So we have the STLTP, the LPTP, and the DSTP, and hold your horses before we go and understand it. So I drew a sketch of what is an ATSC 3.0 system. It might be heavy, but let's explain that. So we have an entity called the Lighthouse. A Lighthouse is a station that has a license to carry and transmit ATSC-free streams or signals. It might be a single transmitter, or it can be a multitude of transmitters if we are talking about SFN. It can carry one PLP or physical layer protocol, one feed, or it can carry additional ones of neighboring stations. This Lighthouse can receive the data. Usually it will be from a cloud playout system, or it can be on-prem, but most likely with the future going, everything will be cloud-based. Now we also have neighboring systems, neighboring stations. For example, on the right, we have an ATSC 3.0 station that doesn't have a license to transmit. It doesn't have its RF transmitters. So this station will go and send it's going to prepare and send its transmission to this station, to the Lighthouse, to be sent over its RF signals. We also have an ATSC on the left, ATSC 1.0 channel sharing station that wants to also participate in the new ball game, which is ATSC 3.0. So it will produce its content and send to this Lighthouse to be transcoded from MPEG-2 to HEVC and so on. But then that Lighthouse doesn't want to lose its business because not many people have an ATSC 3.0 receiver. So it will send its own HEVC content, transcode it to an MPEG-2, and then send it as an ATSC 1.0 to a legacy content station, and that will co-share that on its transmitter. So this is the big ball game that we now see as an opportunity for us to make some good sense and maybe business. So here are the acronyms that we saw. We have the DSTP coming from the cloud. We have the APLP coming from the station. And we have the STLTP running over the microwaves. We're going to talk about those three, but I'm going to put my emphasis on the STLTP because they share commonalities by being almost the same characteristics, and I will touch base on that. So let's understand the acronym. So the data source transport protocol, DSTP, transfers content data associated metadata signaling to a typical IP network from a data source, like a cloud system, to the broadcast gateway. The ATSC link layer protocol, transport protocol, the ALPTP, provides solution for transferring ATSC link layer protocol, favorite code ALP, packets to a typical IP network between two separate devices, which we saw before. And the new studio to transmitter link transport protocol provides a solution to transferring potentially large number of parallel base station packets, data streams carrying content for a like number of PLPs. This is too heavy to explain, but basically STLTP takes everything in and push it through the transmitter. Just to explain more on that, those three protocols, the data source, the DSTP, the LPTP, and the STLTP rely on the capability of encapsulating them into an IP UDP RTP packet, which is great because just like my predecessor spoke about transmitting RTP. So now we have an RTP packet that we can deliver. The RTP packets are quite similar so that a common tunneling protocol can be defined that is common to all three packet types. This common tunneling protocol, which is called the CTP, is used to hide the details of the various tunnel packets by treating them as the payload data. A common tunnel consists of an RTP unicast or a multicast in an IPv4 packet stream based on the DSMBT 2022-1. And the packets are also fixed size, which is also makes our life much easier to deal and transport them. Because they are 2022-1, then we can apply RTP FAC on that and provide basic RTP packet recovery, but we can also apply some ARQ, and that is what I'm going to talk about. It is now possible to add reliable stream delivery protocol like RIST, SRT, and other proprietary protocols to supplement the delivery over challenging network conditions and create new application and use cases. Below me, you can see a diagram how the data flows left to right. So let's touch slightly on the bits, because this is the thing that you need to keep in mind. Basically, the A324 specification, which is talking about the scheduler and the STLTP, basically made three major modification in the packet. Number one, they utilized the M. In the RTP header, you have an M mark flag, and they utilize it to be used as tunnel packet start indicator of a payload. Don't worry, I will show a diagram to explain that. The SRC field was renamed to be used as a packet offset, and the timestamp is replaced, and it's different usage based on the application. DSTP and LTP use it from different one type of timestamp, and STLTP does another usage. It also changed the payload type to signal to the user what is the type of payload being transmitted. Sorry. So this is in a nutshell. Basically, we have encapsulated packet. We have an RTP header. If a mark bit is set to 1, then somewhere in this packet, a new packet is starting. So we need a packet offset, which is the old SSRC field, to find where to start. This packet can this tunnel packet can be stretched over additional packets. So then it will cross over to the next packet. And if a new one packet starts, there is another indicator that here is another one, and so on. So let's see how does that. So basically, now we can have, in order to deliver STLTP, which is IP based, we can change that into a reliable tunnel. Why do we want to do that? We want to do that because we want to enhance the capabilities of ATSC 3.0 and the operational efficiency of doing so. Because now, not only that we can carry STLTP, which is the standard practice, we can add any type of data, just like my friend Sergio showed in his presentation about the tunnel. We can send any type of data. In here, we can send NTP, monitoring, and remote access to the transmitter side. And we can add some control. Maybe somebody want to control the remote side, the transmitter side, the exciter or other devices. He can do that by way of a tunnel. Now, if we will use a RIST tunnel, main profile RIST tunnel, we also gain the joy of authentication and security for the link going through the microwaves. So it's an added benefit. So now we have a more reliable and secure application that we can use in this example with RIST. Other protocols will probably, like SRT, as soon as SRT 1.5 will be available, those may be used for this application as well. So let's go forward. Now, why reliable delivery is so important? Let me start with this diagram. Coming from the SRT documentation, I have nothing bad against SRT, but the common perception is that reliable delivery, what its main task is, take the source, transfer it over a network, and replicate the source behavior on the output. This is great when you're doing IP and you have a lot of buffering and everything is fine and dandy. But when you deliver precise signaling and the exciter doesn't have big buffers, that becomes a problem. We cannot replicate source behavior to the destination because sometimes the source is the studio. It has a studio backbone. Other users, you get a jitter. You don't want to convey that jitter to the other end. Instead, what you want to do is take the source, natively pick up the feed, deliver that to the tower, but try to reduce the jitter and output that as a CBR output. Because it was conceived as a CBR, it should be played as a CBR on the output going to the exciter so that the exciter buffer will not overflow or underflow, and you need to pace it. That is one of the changes that one should care about when designing such a system. You can't say I'm just using a RISC and RISC will solve that because RISC doesn't care about the exciter. You need to have an application aware design to do so. So now let's see some deployments. So we started with a microwave. We have a primary microwave. How about adding another one? Let's do what my predecessor spoke about, SMPTE 2022-7, seamless switching. We have an A path, a B path, and we seamlessly stitch that. So if we have weather condition or lightning hitting one one RF or microwave dish, then the other one will pick up. But that may be too expensive, so why not use the primary one and send only the ARQ over the backup? This is something that you can do, for instance, with RISC. You can send only the ARQ packets on a need basis, so you don't consume that much on the backup, and that can be utilized for other applications, like, for instance, HQ traffic, data traffic, and so on. So you don't need to utilize that much of its bandwidth. Let's now supplement it with IP. Everything is IP, so we can still stick with our microwave, but now we can supplement that with an IP internet. It will do the same job. You can stream it as a constant or on a need basis, and you can utilize any type of link. You can use wired, cable. We spoke about 5G and the ability to use 5G. And why not use Starlink, the new kid in the block in the US that promises the delivery of 50 to 60 megabits. Now it becomes viable. Indeed, there is an additional delay, but you can cope with that in the receiving device to buffer that so that you still get a seamless delivery and you have an operational transmitter. Or you can go all-blown full IP. You have an A path, B path, and you can play with that. You can build the system of your dreams. Just like we saw earlier, we have Kiran showing an A path and B path sending. We can do the same thing, and we have a continuous service running using standard IP networks, high-end, low-end, or mid-range. Now I'm switching to a new application. Let's go to SFN. With SFN, we have the transmitter. He needs to deliver the content to multiple transmitter towers. We can now do the same thing. We can mix microwave and IP. On top, on the blue line, we see the microwave application. And in the green, we see the same thing with IP. So once again, we can deploy in very easy and efficient SFN application, signal frequency network application that can be easily deployable. That is a new thing that we can use this the reliable delivery. You can go in all IP. Now you can have a primary station and a DR station. Maybe it's a nearby station, a remote station, or maybe it's in the cloud. It may be operational on a standby. So if and only if the main studio station, local station goes down, then it kicks in. But the ability is there to kick in, provide disaster recovery, so that your SFN service continues. So finally, let's summarize that and see how all these components are looking. So in this diagram, I showed the one that we started, and we added all the different elements. Now we supplement the STLTP with a backup, so it have a continuous service. The ATSC 3.0 station now can use the internet or any IP link to send an A path and B path to the Lighthouse to be delivered for ingest and then putting on over the air. The Lighthouse itself can set it on an A and B path to the channel sharing station. Continuous service is provided. Also, using the tunnel, one can have confidence return, so that the station can see what reach the channel sharing station. If you want to share the content locally, once again, the A and B path come into play. You send that in, and that sends the signal as an STL to an ATS 1.0 transmitter. To summarize, this is a new and exciting marketplace where reliable delivery can come into play, add its capabilities, all the bells and whistles that we just explained on other applications. Now we can enrich and add to the ATSC 3.0, and new and additional application can spring in the coming future.